Okay, good morning, everybody, and thank you once again for joining us. I'm Bilikisu Olatunji, the founder and co-organizer of the Abuja Our User Group. So, without wasting much of our time, this is Our Ladies Abuja's meetup. Welcome you once again to the meetup, and we hope you get something good and something to learn more about after the meeting. So, about us. Well, these are the names of the organizers of the group, but we have so many people that are supporting us behind the scene. So I'm Bilikisu Olatunji once again. I'm a data scientist based here in Abuja. We also have Queenette Onwuka, a food technologist. Zinatuddin Mohammed, she's in the public health sector. We also have Ifeoma Egbogah, she's an epidemiologist, same as Mabel Ajumobi Abiodun Ekweno. Then we have the last but not the least, Insika Kudo. She's a big data analyst, also here in Abuja. So today we're going to be looking at coding against cancer. So I'm going to share my screen. So we're going to be looking at coding against cancer using R to detect breast cancer from anthropometric data. So our speaker today is also Ifeoma Egbogah. She's an epidemiologist and a data scientist. I'll go through a little bit about her, but I think we have a lot to really know about Ifeoma. So Ifeoma is a dynamic force at the intersection of science, storytelling, and shipping. So with a bachelor's degree in zoology from the University of Benin and a master's degree in modern epidemiology from Department of Infectious Disease at Imperial College London, she brings a strong foundation in scientific inquiry and data-driven thinking to everything she does. So as the co-founder and lead data scientist at Zilla Limited, a thriving logistics and international shipping company, Ifeoma leverages data to optimize operations and deliver seamless shipping experiences. So bridging borders and connecting communities. She's also passionate about online instructors. She's an instructor, so she teaches data science with R, a beginner-friendly course that empowers learners to unlock the power of data using one of the world's most powerful programming languages, which is R. So through this course, she demystifies data, making tech more accessible to Africans globally. So she's also passionate about empowering women in tech and data. She also serves as part of the organizing committee of Our Ladies Abuja, a chapter of the global Our Ladies community promoting gender diversity in our ecosystem. So in addition, Ifeoma is a children's author with a growing collection of coloring books available on Amazon, designed to inspire creativity and celebrate cultural identity in young learners. A loving wife and mother of two, she is deeply committed to mentoring, teaching, and building solutions that bridge knowledge gaps and create opportunities. Whether she is analyzing data, shipping goods across continents, or teaching budding data scientists, Ifeoma brings excellence, empathy, and energy to everything she teaches. So join me in welcoming Ifeoma Egbogah. Thank you for joining us this morning, Ifeoma.
Thank you, Bilikisu. Wow. Thank you, everyone, for joining us today as we take a look at coding against cancer. I hope I'm able to do justice to this topic and show us how we can use anthropometric data to predict those who are at risk of cancer. So if I'll share my screen briefly.
You can go ahead.
Okay. Okay. I believe we can all see my screen.
Yes.
Okay, thank you. So today we are looking at coding against cancer using R to detect breast cancer from anthropometric data. So October, as we all know, is Breast Cancer Awareness Month. It's a time that it's a month that is celebrated globally. It's a time to raise awareness. It's a time to uh, honor those whose lives have been impacted, not just their lives, but their families, their friends that have been affected by this disease, breast cancer. So today in this webinar, we are going to see how we can bring data science and public health and see how we can help, to detect this on time, because we know that survival rate is solely determined or by early detection. Late detection, the survival rates are quite low. So if breast cancer can be detected on time, then there's a higher chance of the patient surviving. So biometric data are routine data that is available at center, and it's something that can be used both information of policy and to help women worldwide. So the theme for this month for breast cancer is every story is unique, every journey matters. So each cancer diagnosis tells a story. It's one of courage, it's one of strength, it's one of resilience. It's also one of hope. Yes, we also see stories of loss as well, But behind every woman that has been diagnosed, or we also know it does affect men, yes, but behind every woman, we know there's a family, there's a community that is trying to navigate through this, because this is not something that just affects an individual. It affects everyone connected to that individual. And as a result, every experience, every story is different, and it deserves to be told. So globally, it's been estimated that in 2022, that 2.3 million women were diagnosed with breast cancer, and we lost about 670. Now, this disparity is obvious more in developing countries, the survival rate. High-income countries have a higher survival rate than low-income countries. And we know that the main difference that we are observing and seeing is basically early detection, timely diagnosis, and also access to treatment, effective treatment. All these are what is causing the disparity in survival rate. So what we are trying to do today is see how we can help with early detection, at least. If it's detected early, chances of survival increases. So let's bring it down home. I know many of us are based here in Nigeria. We do have some outside of Nigeria, but for Nigeria, according to the Global Cancer Observatory, that every year about 28,000 new cases of breast cancer are diagnosed in Nigeria, and we lose close to half of the women. I remember then when I was much younger, this was in the 90s, then there was a family friend of ours. She had twin girls, so they were older than me and they're kind of like my big sisters. And then my mom came and told me that, Ejima's mom has to go to Lagos. And I was like, Ejima's mom, why is she going to Lagos, Because we stayed in Warri then. I was like, why is she going to Lagos? So she was like, she has breast cancer. To me, my little mind, I just, okay, just pop up some pills and, feel better in a couple of days, but not knowing it's something more serious than that, So, and my mom explained to me that, no, she has to go to Lagos and they will have to take out some part of her breast. And in my mind, I'm trying to imagine, take out her breast? What's she going to have then? How's she going to look, Because I'm trying to understand and grasp this disease, how it affects life. One is that she has to travel so far away, which is about 6 hours on the road, 7 hours, and then they have to take her breast out, And then she went for the treatment. It was successful. She came back, but then Every time my mom is a bit anxious and a bit worried, and I'm wondering, it's more like she has to be going to Lagos every couple of months for checkup, to make sure that it doesn't come back, and this continued for a while, But finally, after a couple of years, she was declared cancer-free. And I remember how glad and happy my mom was. So we do know that, like I said earlier, it doesn't just affect the individual, but everyone connected to that person. So more than 70% of breast cancer cases in Nigeria are always detected very late at advanced stages, and this reduces the chances of survival, and treatment options also become quite limited. But that doesn't mean there is no hope. There is a hope. This is a challenge, and as this challenge comes, it also presents us with an opportunity for what we can do as women in data science and as women in tech. So what are we going to do? We're going to turn data into hope. This is where data science meets health. We can harness the power of data, we can harness technology, and then we can see how we can build models and visualize patterns in this data that can help with policymakers and also help health workers identify at-risk groups early and also to respond effectively. As Peter will say, what gets measured gets improved. So for today, given the data that we are working with a categorical data where we have the women grouped into two groups, patients and healthy patients. So a classification model is best. It's best for such kind of data where we have definite or predefined groups. The model can identify patterns and relationship between our outcome and also some predictors. So the classification models that we have available to us, there are more. We have the logistic regression, the decision trees, random forest, support vector machines, k-nearest neighbors. For this exercise for our webinar today, we are going to be using the Cumbria breast cancer data set. It's a data set that was collected at the hospital from women that were just newly diagnosed with breast cancer before any treatment has commenced. And so this data set contains about 64 patients with breast cancer and 52 healthy controls. Altogether, 10 quantitative predictors were collected from the subjects, the women, and this is mainly from routine blood analysis. So basically, anthropometric data is just measurable physical characteristics of the human body, things that we can measure. And with this, we can use to build a predictive model to help us know those who are at risk of cancer. So in this data set, these are our predictors. We have the age of the women, the BMI, glucose, insulin, the homeostatic model assessment. We have leptin, we have adiponectin and resistin in our data, and also have the column for the classification, those who are healthy and those who are not healthy. So these are the attributes that we're going to be working with. And these are things that are collected from blood tests that are done at the lowest healthcare center, the primary healthcare center, and it's something that with this kind of information, with this routine data, the health care worker can use this to identify those who are at risk among those that use the services. So we are going to import our data into R. We'll clean it up, though our data is fairly clean, may not need much cleaning. We'll split our data into training and testing sets, and then we'll build our model, evaluate our model, and then visualize our results. So we'll be going into R to see, take a look at that. So we're going to be working with a couple of packages that will help us with our prediction. Working with the tidyverse, tidy models, and the Ranger package as well. So we're going to run that into R. I like to set my theme before I start. For any plots I have to have a particular theme, so I usually use the theme minimal. So I'll read in our data. So let's take a look at the data we're working with. Okay. So we can see we have 10 columns and 116 rows. Remember, it's just about 62 patients and 64 patients and about 52 healthy subjects. So it's a small data, and it's data that have been collected, I think, in a space of 2 years or so. So we have age, the BMI, glucose, insulin, HOMA, leptin, adiponectin, resistin, MCP1, and then classification. So since our classification is numeric, when we read it in it, I recognize it as a numeric variable. We're going to have to change that to factors because we are dealing with a classification model, which has to do with categories. So I will use the mutate and the factor, and then put my classification column into factors. If I look at it now, we can see that we now have a factor column, 0 for those who are healthy, and then 1 for those who are sick. Now, before you start anything, any analysis, any model building, you have to explore your data. So let's look at our data, exploring it, and see what we can force, the patterns that we can identify in our data. So since we have most of our variables here are numerical variables, so the best plots will be, we could do a box plot, or we could do a density or a histogram to look at the distribution, how the variables, the predictors are distributed. So using the ggplot, let's take a look at the BMI. Now, BMI basically is calculated from the weight and the height of the patient. And there's this research and studies that have been done. From studies that have been done, it's been said that BMI is closely associated with cancer, that the more heavier or obese or overweight one is, they are at risk of developing cancer, and there are various reasons for that. So let's look at the distribution of the BMI in our data set. So I'm going to bring it out. Yeah, that's it. Okay. So from what we can see, so we are having BMI as low as around 18 thereabouts, to as high as it's above 35. So we have those who are normal weight, and we also have those who are obese and overweight in our data set. But it'd be nice to look at this for the two groups, and see if there's any difference between those who are healthy and those who are have been diagnosed with cancer. Is there a difference in the two groups? So we can do that with the facet wrap in our code, in our previous code, and see that. So we can see there is a difference between the two groups. We can see that the 0 is for those who are healthy, 1 is for those who have been diagnosed with cancer. We can see that it's a bit skewed for those who have been diagnosed. They're having a BMI. Most of them are kind of overweight. And then for those who are not diagnosed with cancer and tend to have, though we do have some who are overweight, it's still skewed to the right, but then we have most of them around the normal weight, which is around the 20 BMI to less than 25 is the normal range. It's a normal BMI, is considered normal BMI. Above 25 is considered overweight or getting too obese. So we can see there's a bit of difference between the two groups, just like it's been shown in studies that BMI does tend to have, it's a risk factor for cancer. We can also look at insulin and see what it shows us. Also look at the distribution for insulin. Let's also look at it with a faster track for both groups and see if there's a difference. So, all right, let's take a look at the plot. Okay. So looking at insulin, we see that same pattern also. It's still right skewed, but then it's tight for those who are healthy. It's tight there and it's a bit spread out, as in we have longer tails for those who have been diagnosed with cancer. We can see insulin levels getting up to 60, you know. So telling me that those who have been diagnosed tend to have kind of a higher insulin in their body. And from studies and research that I have done online, going online and looking at variables that can affect or can be predictors for cancer, insulin is one of such variables, because higher levels of insulin in the blood puts someone at risk for cancer. And this basically means that the body's kind of resistance, and then if insulin levels are kind of high, and then it also implies that most likely that the glucose level is also like the kind of a resistance to insulin. The body is not sensitive to insulin, and glucose levels in the blood sugar also goes up as well. So there's a kind of metabolic disturbance, and this increases the risk of cancer. So things like measuring our insulin levels and checking it routinely and seeing if there's change in it, it's something that can help, identifying those who are at risk. You can see it's fairly stable for those who are healthy. It's just between 0 to 20, though we do have but a couple, one or two people that are above 20, but mostly it's less than 20 compared to those who have been diagnosed. We're getting a lot of extreme values there. So these are basically, if you go through all the other variables in our data set, you tend to see the same pattern. Even for glucose, the levels of glucose tend to be higher for those diagnosed with cancer, and it's kind of tightly compact in those who are not. The same for the resistin. Now, all these are associated with BMI to some extent. The resistin, the adiponectin, the higher or the more body fat someone has, the levels of these things also increase in the blood, aside from the adiponectin, which tends to have a protective effect. If for any reason someone's BMI increases, the levels of the adenopectin tend to drop. So it has a protective effect. But then you begin to have issues for people who are overweight, and then these levels, what is meant to protect them begins to drop. So these are some of the variables that we are working with, and there are things that can be measured in the blood sample anytime the patient comes into the hospital, and it can be kept. It could be the patient's history, over time. So now for the prediction, before we start any machine learning or anything, you have to first of all split your data into the training and testing data set. And the whole idea is to make sure you're spending your data well, and you don't want leakage, from your training to your testing. You don't want your model to see your testing data set before before you even decide on which model is best. So normally we split the data into two, the training and the testing. So in R, we use the function called initial split to do that. So we are going to split proportion of 7, and we want the distribution to look like classification. So the same number or the proportion of healthy and breast cancer patients will be the same in our training and testing data set. We can call this, let's call this cancer split. Okay, and then if we take a look at this, we can see it's kind of like a nested data. So it split our data into 70-30. So we have 80 in our training data set, 80 rows, and 36 rows in our testing. So our data is quite small, as we can see. Then to get out our training data set, we use the function called training to do that. Get it from our split. And the same for our test data set. So we run that and we get our training data set. We can take a look at it, see it, using the view function. So this is our training data set, 80 rows with all our predictor variables and then our outcome here. Okay. So given that our data is quite small, we could do some cross-validation in the sense that we split our data into some folds and then pick out some we want to keep in our assessment and some for our analysis. And R, we do this a bunch of times, creating a number of folds. So it's kind of like we're going to have a lot of mini data sets for us to work with, which helps to improve our model as when we try to predict on the data to prove the assessment of our model. So we'll do using the V fold, put in our data, the cancer train, and then V5, let's call this cancer folds. So we just want to increase the number of data we are working with in a sense, if I may use that. So we'll use the number of folds we want. We want 5 folds. So for 1/5 of these will be put in our analysis, and 1/5 to be used in the assessment. So you can increase your V to any numbers you like, usually between 5 to 10, depending on your data sets, the size of your data set, but we'll be working with 5 here. So we have these folds. We can take a look at it to see how it looks. So you can see it split our data where we have 5 folds, and in it we have 64 for analysis and then 16 for our assessment to test our model. So it did this a couple of times, randomly picking the data set to include. It did it 5 times for us. So kind of having like a robust data to work with. Now we want to build our model. So for this exercise, we're going to be looking at two models, the logistic regression, which is like a linear model, but our outcome here is a categorical variable, which is our classification column. And we'll also be looking at the random forest. So before we can do that, we need to specify the type of model we want to run, which is logistic regression. And then we set the engine. I think that engine is basically the package that will be used for where the function for the logistic regression is found. It's in the GLM package. So we can call this counselor. And then for our random forest, so we need to set the mode, which is by doing, since our data, our outcome is categorical, so it's classification. And then the engine, basically the package. So now we're going to be using the Ranger. And let me call this okay. So we have our models set for us now. Then next, we put up a workflow. So workflow, I normally like to look at it as a handbag, where I can add things and take things out, So with the workflow, I can add models, I can add my formula that I want to fit in, I can take out variables, if I did any feature engineering, I can add the recipe to it. So we'll create a we're not going to do any feature engineering basically on this data. We don't really have missing data. And the data is fairly clean. So there's nothing much for us to do there. So our workflow, we just add our formula. Since we are creating two models, I won't add a model in the workflow directly here, but add a formula, which is classification, which is our outcome that we are interested in. Classification and our variables. Now, the dot basically means I'm using all the variables in my data set for my prediction. So that's my workflow. I run that. Now to this workflow, I can then add the two models that we are working with today. So I call it up again. Let's call it up again, the cancer workflow. And then let's add our first model, which was the logistic regression. And then we want to fit. Now, since we are working with, we did a resampling when we created the folds, when we carried the cross validation, I'm not going to use the fit function. The fit function will be if I want to run my model against the training data set, just that. But since I did a resampling, I'm going to use the fit resamples function so that it's able to run the model on the different folds in the data. So the resamples, that's the data we are working with, is as cancer folds. And let's just set a bit of control so that we can save our predictions and all that. And let's put up verbal so we see how it runs. Okay, so let's give this a name. Let's call it cancer fit. Cancer fit log. So we'll run this so we can see it's running. I'm seeing it. Okay. Let's do the same for random forest. Let me just copy this. Change the name, then change the model you're working with. And okay, so our model has run against our data and also with the outcome and the predictors. Let's collect our metrics. Let's see. We want to know which of the model is better between the logistic and the random forest. So okay, so we see from logistic regression, we are having an accuracy of 7 and a ROC of 0.79, and the Brewer class, that's out of bag. How many it got wrong? About 20%. So let's compare that with our random forest model and see. So here we are getting an accuracy of 72 and ROC of 0.8. So basically, it seems our random forest model is better, is doing better. But the difference is it's not much, but in terms of the error, yeah, it looks like the random forest model is doing a better job, at understanding our data and the relationship between outcome and predictors, and you're going to do a better job predicting those who are at risk and those who are not. So we'll use the random forest model going forward, since from the metric we see it's better than the logistic regression. So okay. So now we have that, we can do a confusion matrix to see how many it got right and how many it got wrong. We can do that to take a look at it. So since we did sampled, so from the resampling, we know that we have 16. If we go back to the folds when he shared it, we had 64, 16. So let's see how many it got right in predicting which class. So 1-1 means those who have been diagnosed with cancer. So it's saying the frequency is about 6, and those who do not have is 5. So these ones are rightly categorized. These ones are the ones he got wrong. So basically our false positive and false negative. So we're having about 2 there. So that's what how well our model is doing. We can then also, since we've seen that the random forest is a better model, so we're going to go that to use on our test data set to see how well it will work in predicting those who have cancer and those who do not have cancer. So we're going to call up our workflow again. Our workflow. Now we add our model to it, to the workflow, which is going to be the random forest model we've been working with. We said it's better. And then we'll use the last fit function which is basically, it's going to run the model on our training and then run on our testing data set. And then from there, we'll see how well this model did in predicting cancer. So last fit will be on our split data. Let's leave this. Okay, let's look at it. Let's give it some time. Okay, so here we have a metric. We have, this is kind of a nested, it's nested because of the way our folds are, this data we are working with. So we have our metrics, we have our predictions, because I told you to save predictions here when we ran the fit resamples function. And then we have our workflow. So we can take a look at these predictions, how well our model did in predicting, and also we can then look at a plot, of this prediction. So let's quickly do that. So these are predictions here. So this is our base. Um, okay, So we have here our mosaic plot on how well our model did in classifying those who have cancer and those who do not. Let me bring it out. Okay. So this is the confusion matrix, a mosaic plot for it. So those under one, the rectangle represents those that were really diagnosed with cancer, and our model says, yes, these ladies have cancer. And then this one over here, the 0, are those who do not, and our model got it right. So over here in these two smaller rectangles are false positive and false negatives. So we have those that do not have cancer, and then our model is saying that they do have cancer. That is basically a false positive. And then we have those that have cancer, and the model said they do not have cancer. But basically, this is a plot to see how well our model did in classifying those with cancer. We can also look at the area under the curve, and as well as the accuracy of this of what we just ran now, to know how well our model did. So Okay, so let's quickly look at that, how well the random forest model did.
Hello, Ify.
Yeah,
Okay, you're there.
okay, all right. So we have a random model collecting the predictions and then want to do the ROC curve for that to take a look at our model. So we want to know if our model is just guessing, that's what the ROC tells us. Is it just guessing or is it actually doing something that makes sense, So this straight line from the origin here is basically if those lines rest on it or are close to it, it basically tells us that it's random, it's just making a guess. But the farther away it is from this line, it means the model actually can differentiate between those who have cancer and those who do not. I can see from the various folds that it's doing a good job, at least it's away from the line, given how small our data set is. It's away from the line, and then we are getting a prediction of around 0.7. That's what our ROC is from this random forest. So basically, we are getting a bit of sensitivity there for it to differentiate those that truly have cancer. So that's what the ROC curve tells us here. Our data set is quite small. If we had a robust data, it's just 100 and something patients. If we had something in the thousands, we may get something robust. Though we try to do the cross validation to increase the performance of our model, but then we can see that for this case, yes, it did a fairly good job. So with this, we can then, if we have a data that our model hasn't seen at all, a clinical data with ladies with these measurements taken from them, from their routine blood test, and we put this model there, this model can actually categorize these ladies into those who are at risk and those who are not at risk. And then the doctor can then, do up a follow-up, a consultation, and then, to ensure that if for any reason any one of them do develop cancer, though we don't want that, is detected quite early, and then treatment can also start. In our world where we access to these machines either far away from us for those in the rural area, like the story I shared of a friend that had to travel down to Lagos, this can help, at the basic level, at the local government level, at the grassroots level. So that's it on coding with R, to able to detect and predict those who are at risk for cancer. Thank you very much, everyone. Over to you, Bilikisu.
Okay. Okay, that was wonderful. Thank you so much. Thank you so much. Thank you. And you really started with a good inspirational story there. So thank you so much. So do we have any questions, comments, observations? Okay, go ahead, Abiodun.
Thank you very much, and thank you, Ifeoma, for the presentation.
Thank you, Abiodun.
Yes, I just have some feedback, not necessarily on the methodology, but also on breast cancer generally. So first to state that I think it's a very important information that you and resource, like using anthropometric data. But just to delineate that, anthropometric data are physical measurements, but things like insulin resisting and some of the other factors that are there are not anthropometric, but they are metabolic factors. And then also because when we're talking about cancer generally, there are modifiable and non-modifiable risk factors. So I think if you are using machine learning to look at those factors, then it is good to actually, how would I say it now? Bring in as much of those factors that you have to actually make a decision. Because if we are looking at machine learning, it's the amount of data that is brought in and how rich the data is. That's how good the decision will be. And also to state that even though there might be correlation association, you cannot say that it's really causality. That means you can't say this is the main causal factor for breast cancer. So even while we are using this to try to delineate cases, there are people that will still fall outside the extremities. So far, the only causal element that has been really linked to breast cancer is the gene, because these genes are part of the body. So the BRCA gene, BRCA gene, is one of the main causal elements. Like, for example, if you look at the story of Angelina Jolie, her mom died of breast cancer, her auntie died of breast cancer. And when she found out that she had two genes expressing for that, she actually opted for a mastectomy. And since then, she didn't come up with breast cancer. And she also, I think, did a hysterectomy or something. I can't really remember, but I know she did a mastectomy, double mastectomy, in removing the tissues because she sees that she has the genes and she felt that was her best option. So just to state that this gene is the most important factor so far. Yes, other measurements are there, but combined with environmental factors and other factors, for example, use of progestogen and age, parity, these are different things that also. So I just wanted to bring this in, that in coming up with this is using more than anthropometric measurements, and also there are other factors that are not accounted for in this data that can still increase the risk of breast cancer. And usually what is prescribed by us clinicians is that breast self-examination is still one of the most important ways, which is starts outside the health facility, not in the health facility. Thank you.
Thank you, Abiodun, for that. You're quite right that gene plays a factor. And yes, our data is quite small and it's not as robust as you mentioned. But the whole idea for the webinar presentation is just, we know that testing for genes and requires advanced technology, which may not be available and which can become quite expensive for people to go looking at if they have the genes. So this is just something that can just be done, at the local level. But you are right, having a robust data will help improve prediction very well.
Okay, so Julia, thank you so much, Abiodun, for that contribution. We really appreciate it. Thank you. Do we have any questions, comments? Okay. Okay, I'll share the WhatsApp group link now. So okay, Abiodun, you still want to contribute?
Yes, I just wanted to ask you a question.
Okay, thank you. Thank you.
Yes. Now on the methods, like why did you use random forest? I just wanted to know. Sorry, I'm also an epidemiologist, but I really enjoyed the process, looking at the data and all that. But why random forest plots? Are there other ways by which this could also be predicted, just from your own expertise? Thank you.
Okay. Thank you, Abiodun. So I actually showed two models, the logistic regression and the random forest. And when we ran it, we saw that the random forest did better you know. And another thing was the kind of data I'm working with. Some of the variables are kind of correlated with each other, you know, insulin and the hemostatic model assessment. It has a correlation of, though I didn't show that here, it's something I saw when I was doing the exploration data set. It was about 0.9. So random forest can deal with that, you know. It can handle that. If I were to use the logistic regression, I will have to take out one of the correlated variables. So I think that's basically why the random forest, even one of the reasons why the random forest did better than the logistic regression. But there are other methods, there are other ways. You could even do a Bayesian, you know, if you want to go that, you could also do the SVN, you know, and check the performance and see which is better. But for this webinar today, I just chose two to work with for this webinar.
Thank you.
Thank you, Bjorn.
Okay, thank you so much. Okay, I think this is where we'll draw the curtain for today's meetup. If there are no more questions. Okay. Okay, so I'll use this opportunity to thank Ifeoma again. This was really a good one, and we appreciate your support, both as a co-organizer and also member of the Our Ladies Abuja. Thank you so much. Thank you, Abiodun, for that insightful contribution and also the question as well. So to every other person that joined, we are really, really appreciative of your presence, because that makes us really happy that what we're doing is impacting some people's life and careers. So thank you so much. And we're going to get the recording across to everyone via your email and also our WhatsApp group. We're going to share the link to the recording. And if you didn't get any of this, please just check our YouTube channel and you'll see the recording there in less than it's a couple of days, so it's not going to be up to a week. So we'll be able to push it there. So we'll try our best. So thank you, everybody, once again. So we'll see you some other time. Thank you. Bye-bye.
Thank you, everyone. Bye. Have a lovely weekend.
Bye-bye, everybody. Thank you.